Okay, let's take a look at the relationship between the scale factor, perimeter ratio, and area ratio for similar figures. So if we look over here, I start out with two kind of yellow triangles. The first, rectangles. The first one is a 2 by 3 rectangle. Thus it has a perimeter of 10 and an area of 6. Remember, perimeter is the distance around. So we just go 2 by 3 by 2 by 3, and we take 10 steps to kind of walk around. The area is 6. It's got 6 square units there. You can kind of see the actual individual squares. A scale factor of 3 means each side length is 3 times bigger, right? The proportionality constant between the sides is 3. So if this is 2, then this is 6. And if this is 3, then this is 9. Okay? So let's take a look at the perimeter ratio first. Here the perimeter was 10, and now the perimeter is 30. The perimeter ratio is then 30 over 10, right? The big perimeter over the small perimeter, which then leads us to 3. And we notice that the scale factor and the perimeter ratio are actually the same number. Well, that kind of makes sense. The perimeter is the distance around, and you made this side 3 times longer, and this side 3 times longer, and this side 3 times longer, and this side 3 times longer. So hopefully it makes sense that it's actually just 3 times the distance around if you've increased each side length by a factor of 3. So the perimeter ratio turns out to be the same as the scale factor. Now the area ratio is a different story. Here the area is 6. It's 2 by 3. 2 columns by 3 rows gives 6 squares. If you take and multiply the number of columns by 3, now you have 6 columns, and the rows by 3, now you have 9 rows. You actually have 54 boxes, 6 by 9. But if you look at the area ratio, 54 over 6 is equal to 9, which is 3 squared. It turns out that the area ratio is the square of the scale factor, right? You made each side 3 times longer. You made it 3 times as wide and 3 times as long. You made 3 times the number of columns and 3 times the number of rows, which is actually going to give you 9 times the number of boxes, 9 times the area. Okay, let's look over here. Here we have a 4 by 1. It's got a perimeter of 10 and an area of 4, and I used a scale factor of 5. So I made it 5 times as long and 5 times as wide. The new perimeter is 50. The new area is 100. Let's look at those ratios. Again, the perimeter ratio is 50 over 10, which is 5. The same as the scale factor. I've increased each side length by 5, so I increased the distance around by 5. However, the area is 100 compared to 4. It's 25 times the area. Well, yeah, you made it 5 times the number of rows and 5 times the number of columns, so you actually made 25 more little bitty squares, which is 5 squared. Again, the area ratio is the scale factor squared, where the perimeter ratio is the same as the scale factor. I used Excel to kind of do rectangles here to give you a visual, and then I did GeoGebra over here to give you a representation kind of a triangle here. And here I just did a dilation, and we actually did this way back when. So I made a triangle CBD, and I made a point A, and then I said, hey, why don't you go ahead and dilate this? And so can you see what my dilation factor must have been, or what my scale factor was? Well, we already just decided that the scale factor was the ratio of the two sides, which is also the ratio of the two perimeters. If you look here, this one is a 2 by 3 right triangle, and this is 1, 2, 3, 4, 5, 6, 7, 8. This is 8, and this is 2. And then if you counted this would be 3, and this would be 12. And so the scale factor is 4. Well, look at the perimeter ratio. 68.8 compared to 17.2, 4 times as long. Well, each side is 4 times as long, so of course the distance is 4 times as long, right? The perimeter ratio and the scale factor were the same. Look at the area. The area of, actually that did that wrong. It took the area of they took the area of a rectangle or something. I don't know what they did there, but that is certainly not the area of this triangle. I don't really know what GeoGebra did there. I must have plugged in something wrong, or maybe I changed it. I don't actually know. Certainly that it thinks that this area is 16 times bigger, because that's what it would be, right? It wouldn't be 12. This area would be 3, and then 16 times 3 would be 48. I'm not actually sure why it says that. You can just disregard. Maybe I was moving these around. or maybe it's doing something different, but you can see I can move these around and I can change the size, but no matter what, the perimeter is going to be 4 times and the area is going to be 16 times. Okay? All right, let's look at a couple other numerical examples. Okay, what if I gave you different pieces of information? Okay, so what if we were looking at just any general shape? Okay, so you had some shape here, and so this was shape A, and then we were going to make it somehow bigger. And let's say then I knew that the scale factor, this is some quadrilateral A, B, C, D, and let's say that the scale factor to this new one, oh, I don't know, let's use a percentage. Let's say I increased it by 30%. So let's say 30% increase. Well, a 30% increase is actually a scale factor of 1.3. And so I could say, well, what do you think the new perimeter would be? Okay, I could try to, draw this thing, increase that by 1.3, make it 1.3 longer there, 1.3 longer there, 1.3 longer there. I don't know. It's something close to that, right? Okay, so what's the new perimeter of this? How many times bigger is the perimeter? Well, I know that if I look at P2 versus P1, which is the ratio of the perimeter, it's going to be the same as the scale factor. The area ratio, how many times bigger area 2? Well, it's going to be 1.3 squared. And if you take 1.3, square it, you get 1.69. Okay, so that's a 69% increase in the area versus this. Now, if you knew the two perimeters and you knew the two areas, okay, so let's say that we knew this perimeter was 10 inches, and we knew, area 1, and we knew that the original area was, I don't know, 20 square inches. Well, what's the perimeter here? Well, it's got to be 1.3 times bigger. 1.3 times 10 is just 13 inches. Okay, what is the new area? I know that the new area is going to be 1.69 bigger. It's the scale factor squared. So we just take 1.69 times 20, and we get 33.8 square inches. As long as I know the scale factor, I know how the area and the perimeter will increase. The perimeter is going to be the same increase as the scale factor, and the area is going to increase by the scale factor squared. Sometimes they get a little tricky with saying like a 30% increase, which is really a scale factor of 1.3. Sometimes they can give a fraction for that, but again, all we know is that the area ratio is we square the scale factor, and the perimeter ratio is the same as the scale factor. Of course, they can go in the opposite direction. They could give you the area ratio. They could give you this and say something, and maybe they're going to be easy on you and say like 49 over 16. Okay, so then what's the perimeter ratio? If you know that the second shape has an area or a ratio of 49 over 16, you have to take the square root of it to get the scale factor and the perimeter ratio. Okay, so taking the square root of 49/16 is the same thing as taking the square root of 49 over the square root of 16. You can do that separately. The square root of 49 is 7, and that. And again, that would then be the scale factor. We're going just in reverse here. The scale factor would then be 7/4. Again, if you know the area ratio, you know the perimeter ratio is the square root of it, and those two then are the same. And if I then gave you, the big sides, you could find the little sides. That makes sense? If this is, let's call that 28, and we'll call that, 10. If this is the big one, then if I know the scale factor was 7/4 to go this way, then I have to divide by 7/4. So just take 28 and divide by 7/4 and get 16. And then take 10 and divide by 7/4 and get, you're going to get some funky number, 5.71-ish. And now I know all the information. Again, you can go this way. I can give you the small one and the big one. You could find the scale factor, you could find the perimeter ratio, and then you could square it to find the area ratio. Or you could go the other direction. I could give you the area ratio. You could square root it to find the perimeter and scale factor. And if you knew the big one, you could divide by the scale factor to get the small one. Again, small to big, we're going to multiply by the scale factor, assuming the scale factor is something bigger than 1. If it wasn't, then if the scale factor is smaller than 1, then you actually are going to start with a big object and go to the little object. But we know here then, right away, when I gave you this, if the area ratio was bigger than 1, well, then the second one is in fact bigger, right? It's whatever this number is, right? 49, if 49 over 16 is approximately like 3 point, oh, actually it is exactly 3.0625. So what I'm telling you is that this area is 3.0625 times bigger than this. This, as a number, as 7/4 is just 1.75. So the perimeter here is 75% more, or 1.75 times this. And again, you could find the two perimeters and you could find the areas and you could show that to be true. But these videos, again, are all about area ratio and perimeter ratios and how they're related. But they really shouldn't be too big of a problem on this one. Just look at those relationships and kind of answer some of those problems.